Picture this. You're cruising along, everything is perfectly normal, and suddenly, the engine goes completely quiet, right? Now it's just you, the aerodynamic design of your aircraft, gravity, and a tiny patch of pavement waiting way down below. Welcome to this explainer. Today we are breaking down one of the most challenging maneuvers out there, the power-off 180-degree accuracy landing. We're going to look closely at exactly how this works, unpacking the whole shebang from the literal second you pull that throttle to idle, all the way down to a pinpoint touchdown.
Now you might be wondering, how in the world do you hit a perfect, specific landing target when you have absolutely zero engine power to help shallow out your descent or stretch your glide? This isn't just some arbitrary flight test requirement to check a box. No way. It is the absolute ultimate test of physics, spatial awareness, and energy management. You've got a strictly finite amount of energy, and you have to spend it flawlessly to hit your mark.
Okay, let's dive into this. Here's our structured flight plan for today. 1. Targets and runway dimensions. 2. Mastering your energy state. 3. The downwind descent procedure. 4. Shifting the aim points. And finally 5. Troubleshooting energy deviations.
All right. Section 1. Targets and runway dimensions. The strict rules of the game.
The tolerances for a power-off 180 are just incredibly unforgiving. Your touchdown tolerance is exactly -0 feet and plus 200 feet from your specified touchdown point. Did you catch that? -0. If you touch down even one single inch short of your intended target, that's it, maneuver failed. You literally only have a 200-foot box to hit. And to nail it, you've got to factor in that a normal short-field float is about 500 feet, give or take 100 feet depending on the wind. Oh, and if you have a tailwind on final, you're going to need to add 100 feet of float for every single knot of tailwind.
What's really fascinating here is how knowing exact paint dimensions on the pavement gives you a built-in ruler right from the cockpit. I mean, how do you measure a 200-foot landing box at 80 knots? You look at the paint. Runway number designators are 60 feet long, well, except for the 6 and the 9, which are 63 feet. The centerline stripes, exactly 120 feet long, with an 80-foot gap in between them. Your 500-foot markers are 75 feet long, and the 1,000-foot aiming point markers can be up to 150 feet long. Memorizing these dimensions is a total game changer because it means you can visually calculate your exact touchdown distance in real time.
Moving right along to Section 2. Mastering your energy state. Your energy bank account. Think of your energy as an invisible bank account with two types of currency. Our first currency is kinetic energy, which is simply your airspeed. But here's the critical shift in mindset you need to make. Because your engine is dead, kinetic energy is managed entirely by your pitch attitude. When you don't have power, your elevator effectively becomes your throttle. Push the nose down to quote-unquote add throttle and increase airspeed. Pull back to reduce it.
Our second currency is potential energy, which is your altitude and your glide path. You manage this potential energy by deciding your path over the ground. If you turn toward the runway sooner, you spend less potential energy. If you square off your turns and fly further away, you're spending more. Altitude is literally a currency you spend via your ground track, and you've got to constantly guide the spending based on what the winds are doing.
Okay, Section 3. The downwind descent procedure. Applying these concepts.
Let's look at the big picture and see how this all comes together. Tracking the flight path for a Cirrus SR20 G7, you can see it maps everything out from the downwind key position. That's where we pull the power to idle. Through a continuous turn, stepping down through decision points. You're constantly checking that kinetic and potential energy at the 30-degree bank point, stepping down all the way to the threshold, and zooming in on that 1,000-foot marker. The entire maneuver strictly begins at the abeam point. That's the exact moment your wing is parallel to your intended touchdown point. The setup here has two really simple immediate steps. Step 1, pull the power to idle. Step 2, pitch for exactly 100 knots. Boom. By doing that immediately, you're establishing your kinetic energy baseline. You lock in that speed right away so your brain is freed up to focus on managing your ground track.
But, how long do you actually stay on the downwind leg before turning? Well, that depends entirely on the wind. A normal pattern usually involves about a 300-foot altitude loss. But in a power-off 180, you have to adjust based on winds aloft. If the wind is 10 knots or less, you descend 200 feet on downwind before turning. If it's a bit stronger, say 11 to 20 knots, you only lose 150 feet. And if it's really howling, like 21 to 30 knots, you only descend 100 feet before turning base.
Higher winds mean a stronger headwind on final, so you absolutely must turn sooner and descend less on downwind to preserve that precious potential energy.
Let's shift gears to Section 4, shifting the aim points, adding drag via flaps.
So, as you roll onto the base leg, you want to establish a 30-degree bank angle, while maintaining that baseline 100 knots of kinetic energy. So, the crucial point is this. You must constantly judge if your current glide path, your potential energy, is actually going to reach the touchdown point before you even think about touching the flaps. You have to ask yourself, are you high enough? Are you fast enough?
If you judge that your energy is looking good, you add 50% flaps and pitch for 90 to 95 knots. But here is the magic trick of this entire maneuver. Adding drag steepens your descent, which means your visual aim point on the windshield has to move. With 50% flaps, your aim point drops approximately 200 feet closer to the runway threshold. You reevaluate again. If your energy is still solid, you add 100% flaps and pitch for a third aim point. That final setting moves your visual target another 300 feet closer to the threshold. You are essentially stepping your aim point back step by step to account for the drag you're introducing.
Assuming your actual final intended touchdown point is the 1,000-foot marker, all of this aim point shifting leads you right to one very specific keyhole in the sky. And this brilliantly illustrates exactly what perfection looks like. You should be aiming to cross the runway threshold at precisely 50 feet above ground level, carrying exactly 78 knots of airspeed. If you thread that needle, you are perfectly set up to carefully control the round out and hold off phase, and you'll drop right onto your touchdown point.
Finally, Section 5, troubleshooting energy deviations, rescuing the maneuver, because let's be real, things rarely go perfectly.
So, how do we fix it? If you find yourself high and fast, you've got too much of both currencies. You've got to turn away from the runway or overshoot final to increase your ground track and burn it off. If you're high on your glide path but right on speed, introduce a forward slip to just drop that altitude without speeding up. What if you're high but slow? Simply pitch down to trade that excess potential energy for some vital kinetic energy. And if you're on glide path but coming in way too fast, pitch up to bleed that speed off and utilize a forward slip. It is just a constant, rapid-fire mental game of if-then logic.
Now, being low on energy is far more critical because running out of altitude or speed simply means you don't make the runway. If you're low but fast, pitch up and turn in. Trade that speed back for glide distance. If you're low and on speed, square your turn into the runway and seriously consider using the flap balloon effect. You know, that momentary ballooning lift you get right when you deploy flaps. And then there's the most dangerous state of all, low and slow. If you're here, you must pitch down, turn direct to your aim point, and aggressively utilize that flap balloon effect, because honestly, it might be your only rescue to make the pavement.
So, there you have it. We've broken down the rules, the underlying physics, and that crucial rapid-fire decision-making required when your engine isn't there to save the day. The Power Off 180 literally forces you to visualize and actively manage an invisible bank account of altitude and airspeed. So I want to leave you with this final thought. How will mastering your unseen energy state transform your everyday decision-making in the cockpit, even when the engine is running perfectly? Think about that on your very next approach, and keep flying smart.